Okay, hello everyone. Welcome to Module 12, the last module, which is all about wave optics. So I've organized the module on collage into four different sections, and I'm gonna cover the most important concepts from each of those four sections in this one video. So I've sort of like compiled everything into one video this week. And I've integrated some example, like worked problems on what I think are the most important topics that will hopefully help you with your challenge this week. Okay, so part one of this is just like what is like we've building on this idea that we started talking about last week, which is like what is light and how do we model it as a wave as opposed to a particle. Ray optics was when we talked about ray optics, we were of course talking about light as a wave as well, but we were sort of like simplifying it just by drawing it as a straight line. So we'll talk a little bit more, we'll build on that idea. I'll talk more about like the wave nature of light, something called Huygens principle, and then we'll revisit this idea of diffraction and refraction. And then in the second part, we're going to talk about something called the double slit experiment. And we'll show how the double slit experiment was done in the 1800s by a guy named Young, and he used it as a way of showing that light does behave like a wave. So it sort of like illustrates the wave nature of light. And building off that, like what is interference? Like when you have like two waves interfering with each other, you have constructive and destructive interference. And then we'll like build that out to multiple slits and diffraction gratings. And then part three on collage is like instead of talking about double slit, we'll talk about single slit. I'm not going to cover that in the video because in my opinion it's not as important, but it is covered in collage. You can take a look at it and there's a couple of exercises built out to hopefully help you understand single slit diffraction. And then part four is this like very, very basic concept called the Rayleigh criterion, which is basically like how you calculate the diffraction limit of some optical system. So I'll do an example, and then there's a challenge question this week on that, but it's very straightforward. Okay, so just like to get started, the wave nature of light. So there's something that I'm sure most of you have heard of from middle school science, referred to as the wave particle duality of light, which is this idea that light sometimes exhibits wave-like properties and sometimes exhibits particle-like properties. And it just depends on the situation. So this is this idea, let me just write it. This is like the wave particle. I think this is like covered in middle school in most like curricula, like duality of light. So in some situations, you can model light as a wave, like an electromagnetic. It's it's part of the electromagnetic spectrum, which we talked about two weeks ago, right? So all of these pictures down here are depictions of light in that way, like a wave-like properties. And then you can also sometimes, in certain situations, it's more convenient and light behaves more like a particle. And a particle of light is just referred to as a photon. Okay, and a photon is really like a package or a packet of energy. Okay, and usually it's convenient for us to think about light as photons when light is interacting with very small things. Like so, when light interacts with matter on a very small scale. Usually it's easier to think about light as a particle, like a photon particle. Whereas when light is bending or getting distorted as it kind of hits up against different obstacles, it's like diffraction and refraction. It's much easier to think about light as a wave. Okay, and we'll see that in a second. Um, okay. So yeah, these are I want to just make the point that these are three different ways that light is drawn as a wave. Okay, so like you can draw, sometimes you'll see a wave drawn like this. Okay, where each of these things is referred to as a wave front. And like each of these lines is like you can think of each of these lines as like the peak, and then in between is the trough. So it would be like you were looking at, I don't know if I can draw this well, but like it would be like if I turned this wave, like each of these is a wave front, and then the like direction of propagation is in this direction. Okay, so that's what this picture is trying to show. Like this is each of these is like a wave front, right? And then the spaces in between are like the troughs. Okay, so this would be like a view from above, from the side, and then like, we saw this a couple of weeks ago. This is sort of like the overall view. Okay, so and light is referred to as a transverse wave, right? Which means that its oscillations, like up and down, are perpendicular to its direction of travel. So it's like it's moving this way, like in this transverse direction. Okay. Um, so okay, I think that's important to know because like this idea of a wave front comes up when we talk about Huygens principle. Okay, so wave optics, I said this before, becomes essential when light interacts with apertures, so like spaces or structures. Like an aperture is just like a space, an opening. So if you have like a wave front, like hitting up against this aperture, like we want to understand like what happens to the light, like how does it behave? So this is like an aperture. Okay. And when we're talking about this, like we're assuming, and this is like a super important assumption with wave optics. We're assuming that the size of the wavelength, so the length of the wavelength, so if you think of like a wavelength, right? That's one wavelength, is comparable in size to the size of the aperture. Okay, so like if this is some like aperture, let me call it, I don't know, A for aperture. The size of the aperture is approximately the same as the length of the wavelength of the light. Okay, that's an assumption that we're making. Okay, so we're talking about pretty small apertures. Okay, when we're talking about things like diffraction. Okay, so this when we're talking about light as a wave. It obeys this relationship which we saw a couple of weeks ago. Remember, we said that all electromagnetic waves travel at the speed of light, where c is the speed of light, right? And like light is just like a narrow band in the electromagnetic spectrum. Okay, it's like the part of the electromagnetic spectrum that we can see. Okay, but because it's an example of magnetic wave, it travels at the speed of light, so 3 × 10⁸ meters per second, and its a relationship is like the frequency of the light times the wavelength, right? And this should make sense to you because like this is wavelength, right? And this is a length, so this is like measured in meters. And then frequency, remember, is like the number of times a wave passes a point. Like if I were to stand in one spot and then like count the number of waves that go by every second, that would be its frequency. So the unit of frequency is inverse seconds. So if I multiply a meter times an inverse second, when I go like C equals lambda F, this would be like meters times like inverse seconds. So I get back the unit of the speed of light. Okay. So when And we covered this last week, but this is just a review. When a wave enters a medium, like when it goes from one medium to another, so like let's say it's going from air to water, when it enters a medium with some index n, this is super important. The frequency stays fixed. The frequency doesn't change, but the speed and the wavelength change. Okay, so remember we said like that the index of refraction is just the ratio of like the electromagnetic wave in the material compared to the speed of light. Well, if you want to know like how fast a wave is going in some material of index n, you just divide the speed of light by whatever that index n is. Okay, so like say light is going through air and then it hits water. That wave is going to slow down. So it's going to slow down from 3 times 10 to the power of 8 meters per second to some fraction of that, some slower speed. How do I know what the speed is? I just divide it by the index of refraction of water. And then that gives me the new speed, v. Okay. Similarly, like if the wave had like a certain lambda going like traveling through air and then it hits water, the wavelength is going to change. It's going to shorten, right? It's going to shorten when it goes to the higher index, right? Because it's going to get divided by the index of refraction for water. So wavelength decreases by the same factor n. Frequency does not change. So that's why like when light goes into water, like it doesn't change color. Okay, because what determines the color is the frequency of something. And so the frequency doesn't change. Like in this relationship back here, C equals lambda times F. So let me write this here. C equals lambda F. This is basically in a vacuum. To find the velocity of light traveling in some other medium that's not a vacuum, you just have to take the speed of light and divide it by the index of whatever that material is. And then once you have that speed, you can go back to your relationship between wavelength and frequency. But just like the important point here is that when light of a certain frequency goes from one medium to another, the wavelength decreases, assuming that the index of refraction is higher. But that like the wavelength changes, the frequency doesn't. Okay. So let's go on now to Huygens principle. So Huygens principle basically says that every point along a wavefront is a source of what we call wavelets that spread out in the forward direction at the same speed as the wave itself. So let's say that you have some wave and it's traveling in this direction with a velocity v. Okay, and we're representing that wave with like this wave front, which is just a straight line. What Huygens principle says is you can take any point along that line and you can represent it as a what we call a wavelet. So this is a wavelet, just like it's a semicircle. And the tangent of that wavelet will be the new wavefront. Okay, so it's a way of describing how a wave front moves through space. And the reason that it's useful is because it helps us understand things like diffraction and refraction, which I'll show you in a second. Okay, so this S is basically the distance that the wavelet travels, like in some period of time, right? So if the wave is traveling at a speed of v, then we know that v velocity is just displacement over time. So S is the displacement or the distance of that wavelength, like S equals VT. Okay, is the distance that that wave has traveled in that time. Okay, so this is like why it's useful, Huygens principle. So if we think back to refraction, which we covered last week with Snell's law, if you have this wave front, so here's a wave and it's traveling in this direction, right? And remember last week, instead of drawing the wave as a wave front or as a wavelet, we just represented it as a ray, which is why last week's topic was like ray optics. So you've got these like wave fronts and they're traveling. So this is the wave front, the second line for this wavelet. Okay, so like you can represent any of these um like wave fronts as a wavelet. Like if I draw, but look what happens here when it hits the medium. This part of the wavelet is going to not no longer be traveling at the same V as this part of the wavelet. Okay, so like now we've got like try to draw this. Like this part of the wavelet hits the because the ray is coming in, the light is coming in at an angle and it's hitting let's say this is air and this is water. It's hitting the air-water interface at an angle, and so part of the wavelet is slowing down before the other part of the wavelet. So like at this point here, this part of the wavelet is still in air and this part is in water. So this part's going to slow down, which is why the light bends like towards the normal. Okay, so this is a way of us explaining why refraction happens. Okay, last week when we talked about Snell's law, we defined the mathematical relationship of like what refraction is with Snell's law, but we didn't explain like why does it bend when it goes from and why does it bend towards the normal when it goes from an index of refraction that is lower to higher. Okay, and so hopefully like that you see this kind of explains it, right? Like the wave front is hitting the interface and part of the wavelet is slowing down before the other part is. Okay, and therefore the only thing for it to do is bend. Okay, so Huygens principle also allows us to understand what happens when a wave front hits a slit. Okay, so here's a picture of like three slits. So this is like slit number one. A slit is just an aperture, right? So this is a large slit, and this is like a small slit. And what you should notice is that the wavelets bend as they go through the slit, and they bend more the smaller the slit. So the smaller the slit, the more diffraction there is. And diffraction is just defined as the bending of a wave around the edges of an opening or an obstacle. Okay, so what does Huygens principle say about diffraction? It says that the edges of the wavefront bend after passing through the opening, which is what diffraction is, and the amount of bending depends on how small the aperture is. Okay, so like this is what I said at the beginning. The wave characteristics like of light, light behaves most like a wave when the slit, like the aperture, is about the same size as the wavelength, right? Which means like that this aperture would be very, very small. Okay, that's when you're going to see like the most bending or diffraction. Okay, if we define like the aperture as A. Okay, so I mentioned this at the beginning. There was this experiment done that basically proved that light behaves as a wave. This was like the Young double slit experiment. And basically, what Young did was he took pure wavelength light, which means like light that is just all at one frequency. And he sent it through a pair of vertical slits. And Um, on this, and there was a screen on the other side, and what he saw was this like alternating like light and dark, light and dark pattern. Okay, so it's like, you have these like light bands, and then in between them you have these like, so that's a light band. In between them you have these like dark bands. Okay. And this basically showed that light has to be thought of as a wave in some situations, because if you could only conceive as light as a particle, then what you would have seen in this experiment was just like I mean, what he in fact like thought he would see, if these are the two slits and this is the screen behind, he thought he would just see like two bright bands. Right? If you can only model light as a particle, then that would be what would happen. Right? So like the fact that he saw these like alternating light and dark bands meant that there had to be some interference happening between the wavelets. And then that interference pattern is what's causing like the light and dark bands that we see. Okay, so that's basically like this is sort of just defining. I think like probably everyone is familiar with this idea, but like I just want to review it. So let's say you have two waves, and they're traveling through space, and they're coherent, which means that they are in phase with each other. Like when the in space, their peaks line up at the same place, and their troughs line up at the same space, right? So these are referred to as coherent waves. Um, so when you have two waves like this, they constructively interfere. Basically, like their peaks add, interfere, and their troughs add. So like if the amplitude of each of these waves is x, the amplitude of the resultant wave would be 2x. Okay. If you have waves that are half a wavelength out of phase, which means that like the peak of one lines up with the trough of the other, then you get destructive interference. So this is like, and sorry, I should have said up here, this is 100% constructively interfere. And then down here, when they're a halfway lambda out of phase, this is 100% destructive interference. Okay, so basically like the peak of wave one cancels with the trough of wave two, and you just got like a flat line interference. Okay, so like let's go back to the double slit experiment. So the double slit experiment showed these like this is what the pattern looks like. This is like what we call the interference pattern. Okay, like if you actually had a screen and you were in a dark room, and let's say you took like a laser and you shone it through two slits like this, what you would see is this pattern on the screen. Okay, which is pretty pretty incredible. Right? So like the reason that happens is when these wave fronts hit the slits, the waves the each wavelet bends. Okay? And then those wavelets propagate through this space basically uninterrupted, right? And then they interfere when they reach this screen. Okay, so like if you think of it as like two waves traveling slightly different distances because of the fact that they bend, and that difference in distance allows them to add up either constructively or destructively or somewhere in between. Okay, so that's basically what this picture is showing. It's got, like these are each of these are like the wavelets as they spread out from the slit. Okay, and then like, so the wavelet, like each of these is like a wavelet at a different point in time. Okay, and then when they reach the screen, they add or subtract, depending on how out of phase they are. Okay, so we'll look at the math behind that in a second. But this is basically like what I just said. So here you've got like the two slits, you've got the waves going through them, and then when they hit this screen, if they are out of phase, right? So if they're like lambda out of over two, like out of phase, then they destructively interfere. If they're in phase, like if their peaks line up and the troughs line up, then they constructively interfere. Okay, so what determines that? Like whether it's a destructive band or a constructive band, it's basically like the path, what we call the path length difference. It's the difference in um like it's this distance here, this like path length difference. Like how much further does the wavelet coming from this slit have to travel compared to the wavelet coming from that slit? Okay, and that's like basically here, and that path length difference determines whether it's like in phase or out of phase. You can actually see it much better here in this picture. Okay, so S1 is slit one, S2 is slit two. Little d is the distance between the two slits. Okay, so let's say you've got like this is a ray that represents the path of the wavelet. Okay, and that's coming from slit one, and this is coming from slit two. Okay, so I think you can see that like if I extrapolate those lines all the way to the screen, the light coming from slit two travels a slightly longer distance than the light traveling from slit one, right? And that distance in this picture is called delta L. So delta L is like the path length difference. Okay, and that can be calculated by just because I know if that angle theta is sine theta, then sine theta um, is just going to be opposite over hypotenuse, so that's delta L over D. So sine theta D equals delta L. So sine difference or sine theta times D equals the path length difference. Okay. Now this is very cool because now that we know what that path length difference is between two slits that are a distance d little d apart, we can start applying some conditions for constructive and destructive interference. So remember this is equal to the path length difference between the rays going through the top slit compared to the bottom slit. If that path length difference equals some integer multiple of lambda, then this is a constructive is a constructive band. It's a bright band. Okay, so like if it's constructive, if d sine theta, the path length difference, equals some integer value of lambda. Okay, because that's the condition for constructive interference. It's going to be a destructive, so like let's say there's some other point here where the path length difference, d sine theta, is some half integer multiple of lambda. Then it will be destructive. Okay. And I mean, to be honest, that like these two equations for this one for constructive and this one for destructive is the most important thing, I think, from this like wave optics section, because you can apply this idea to like all of the anything that has a slit. Okay, so like we can extrapolate this to multiple slits. Um, and with a small kind of mathematical deviation, we can also extrapolate it to a single slit. So, although the equation that governs a single slit is slightly different, and I've put that in collage, but I'm not going to cover it in this video because in my opinion it's not as important. But if you, as long as you understand this for the double slit sort of situation, then you can easily extrapolate it to multiple slits. Multiple slits, it's the exact same multiple, it's the exact same mathematical relationship. Okay, so what does the interference pattern look like? Well, it looks for a double slit situation, it just looks like this. You've got this like super bright, intense band right in the middle. Okay, this like very like tall peak. And then each of these is like a slightly less intense. This plot here is basically in the light intensity. Okay, like the red line here represents intensity. So like the higher the peak, the more intense or bright the light is. Okay, but basically what you see is an interference pattern for the double slit it has an intensity that falls off with the angle. So like the brightest slit will be right in the middle, and then each of these bright bands will be slightly less bright than the one. It gets like less bright as you go from like the middle to here and the middle to here. Okay. And then okay, so that's the double slit. There is a small angle approximation that comes in very, very handy. So let me explain that to you. So um skip ahead am I all right, so let's simplify the diagram that I just showed you. Um this is the relationship that I just introduced. So this is going to be like where this is going to be like constructive interference. So where this will be like where a bright band appears when you have two slits that are a distance d apart. Okay. Um, if the if the let me define this distance from the slits to the screen as L. Okay. In the case where L is much, much larger than D, you can make you can make this simplification. Okay, so so we've already seen from this equation here that sine theta, if I rearrange that equation, sine theta equals m lambda over d. Okay, um, if L is much, much larger than D, I hope you can see that, let's say I define this distance here. Let's say this is the distance to the first bright. So this is like the first bright, like fringe. Okay, the first bright spot. Let me define that as Y. Okay, so assuming that the distance to the screen is much larger than the distance between the slits, you can say that tan theta equals y over L, right? It's kind of because like as as these two um, points get closer and closer together, um, the only triangle that we need to consider is like this one. Okay, like imagine that, let me draw it in a different color. Imagine that these two points converge to this to the midpoint here. Okay, let me change colors. Okay, so like basically the in the limit where D goes to 0. Okay. The only triangle that matters is that one. Okay. So if this is theta, then tan theta is just y, like opposite over adjacent, the distance from the screen to the slits. Okay. So um, in the small angle approximation, sine theta is basically the same as tangent of theta, like as that angle gets smaller and smaller, which is the condition for, this. So we can say that m lambda over d, which is equal to sine theta, equals y over L. Okay? And that allows us to say that y equals m lambda L divided by d. Okay, which is this equation here. Okay, so the distance, this is the distance to like a bright fringe at order M. Okay, so like let's go back to which picture? Okay. Each of these is, well, maybe it's easier to see it in this picture here. Each of these is an M. So like this, like central one would be like M equals 0. This is M equals 1, M equals 2, M equals 3. Basically each fringe is like an order, like as you go from the central to the higher fringes, M changes, like M gets larger. Okay, so like if you're trying to calculate the distance to like the first bright fringe, then M would be equal to 1. Okay, so this would be like Y1, and then that would just go to 1. And then that would be like how far up the screen, how far from the central spot is the first bright fringe. Okay, the central one is just referred to as like the central fringe. Okay, so this formula here is just the distance between bright fringes or dark fringes. Okay, because they're evenly spaced. So like it's the distance between, so it's like from M1 to M2. Okay, so the distance between bright or dark fringes. Okay. So I think, I mean, to be honest, this is easiest seen in an example. Um, So let's look at this one. Suppose you have light from passing from a helium neon laser through two slits that are separated by a distance of 0.01 millimeters apart. And you find that the third bright line on the screen, so third bright line, you think, oh, M equals 3. Okay, is formed at an angle of 10.95 degrees relative to the incident beam. So the incident beam is that one in the middle. What is the wavelength of the light? Okay, so I always like to draw everything. So let me draw like so those are the two slits. Okay, so there's like slit 1, there's slit 2. Okay, the distance between them is 0.0 0.01 millimeters. Okay. And let's say the screen is over here. And um, so what are we told? Oh, the angle. So let me draw like the central spot here. The central, so the angle from there to there is 10.95 degrees. Okay, and I mean, I should have drawn it so that, I mean, th this ray is obviously coming through the slit. Okay, so I didn't draw this very well. Let me redraw it. So so you've got that, and then there's the central. Okay, and then that's that angle there. Okay, so, all right, so we want to know what is the wavelength of the light. Okay, so I know this is a bright fringe, so therefore the relationship that governs it is d sine theta equals m lambda. And I'm trying to find the wavelength, so I'm going to solve for lambda. So lambda equals d sine theta divided by m, where m equals 3 because it's the third bright line. Okay, so this would be like the third bright line here, the third bright fringe. Okay, or line, whatever. Okay, so and the now I just plug in the numbers. 0.01 millimeters is the distance between the slits. Sine of 10.95 degrees. And then because it's the third order, I divide it by 3. So this is going to be 6 times 10 to the negative 4 millimeters, which is 633 nanometers. And if I was doing this as a challenge problem, I would probably note in my evaluate result that 633 nanometers is the wavelength for red, which makes sense because um, like neon signs emit um like that frequency of, or sorry, that wavelength of light. So that would be like the wavelength emitted by a neon light, which makes sense because this is a helium neon laser. So it would be like a red light that we'd be talking about. Um, okay, so that is an example that hopefully just gives you an idea of how this works. So let's look at a second one. So in the second one, we've got 532 nanometer green laser passing through slits separated by a 0.3 millimeter like separation between the two slits. The screen is 1.8 meters away. Find the fringe spacing in air. Okay, when you see a thing that says fringe spacing is just basically like this. It's code for delta Y. Okay, fringe spacing is delta Y. It represents the distance between adjacent bright fringes or adjacent dark fringes. Okay, like the spacing between two bright fringes is going to be the same as the spacing between two dark fringes. Okay, it's just a different equation that governs their location, right? Like this one is for bright fringes and this one is for dark fringes. Okay, but the spacing between adjacent bright or adjacent dark should be the same. Okay. So, okay, so that's what that question is asking for. All right, so let's draw it. So let's say that I've got my two slits. Okay, and I've got my screen over here. Okay, and I want to know basically like the distance between two adjacent bright uh, fringes. So I could find the if this is like m equals 0, the central like really bright one, and this is m equals 1, I could find like the distance between those two fringes. Okay. And then like that distance is going to be the same as like between m equals 1 and m equals 2. Okay, so I know that, let me change colors. I know that this distance is L 1.8 meters. Okay. And I know that the distance between two adjacent fringes is just based on my small angle approximation that I explained earlier, right? Like the 1.8 meters is much bigger than the distance between these two slits, which is like tiny. It's 0.3 millimeters. So like the L is much larger than D. So I can assume that the distance between bright fringes, delta Y, is just equal to lambda L divided by D because of my small angle approximation. Okay, so now I really just have to plug the numbers in, right? Because I'm told that it's 532 nanometers, which is 532 times 10 to the negative 9 meters. And then I'm going to multiply that by L, which is the distance between the slits and the screen. So that's 1.8 meters. And then divide that by the distance between the slits, which is tiny, 0.3 times 10 to the negative 3 meters. Okay, and so that gives me a distance of 3.19 millimeters. Okay, so that's part A. Well, the question also asks, calculate the new spacing if I were to put this whole apparatus in water. Okay, let's call that part B. So in water, the frequency stays the same, but the wavelength of the laser light changes. Okay, the laser it's going to get smaller, right, as the laser light slows down in water. So the water the wavelength, let's just call it the new wavelength n, is going to be the old wavelength divided by the index of refraction of water. So that's 532 nanometers is what it was in air, the laser light in air. And then I'm going to divide it by 1.33, which is the index of refraction of water. And I get a new wavelength of 400 nanometers. So that like green laser is going to have a smaller wavelength as the laser light slows down. Okay, so I would just like plug that back into my formula, delta Y equals like the new lambda times L over D. And if you do that out, you got like the 2.4 millimeters. So like the fringes are going to be closer together when this whole thing is underwater compared to when it's in air. Okay, another way you could have calculated that is you could have just taken your delta Y from here and divided it by the, so like, or you could take your delta Y and just divide it by the index of refraction of error. So you could take like your, what was it, 3.19 millimeters, which was the fringe spacing in air, and just divide it by 1.33, which is the index of refraction in water. And you get the same thing as what you got before, 2.4 millimeters, which is the fringe spacing in water. Okay. So now let's talk about multiple slit diffraction. So multiple slit diffraction is the exact same as double slit diffraction. It's just you get a slightly different pattern of fringe. Okay, but the equations are the same. Like so, if you look at this picture, And a you've often heard this diffraction. Like, what is a diffraction grating? A diffraction grating is just something that has many slits that are evenly spaced. Okay, so like this here is a picture of a diffraction grating. So when you pass coherent light through a diffraction grating, you get this kind of a pattern. The maxima, so like the the delta Y is the exact same as with the double slit. Okay, so like the equations are the same. Like the d sine theta equals m lambda for constructive. So the dark, or sorry, the bright fringes are going to appear at this condition here, just the same as the double slit, and the d sine theta equals m plus is the same for the construct. The equations are the same. Okay. It's just you got this like kind of separation. So like actually you can see it really well here. This is what the pattern looks like when you have a double slit. This is what the pattern looks like when you have a grating. So you have these like and you notice like that the central peak is lined up in both situations, right? Which is what I said before, like the delta Y, the fringe spacing is the same, but you have this sort of secondary structure with the grading where it separates out all the colors in the higher order patterns. Okay, which is what we see with these like little like smaller bumps here. Okay, so like for if we send like light through a diffraction grating, you see that the maxima, which are these peaks, they appear at the same angle as with the double slit. But for the diffraction grating, the peaks are narrower and therefore sharper. Okay, and you also see sort of like this like rainbow like effect. Okay. I mean, again, the easiest way to see this is with an example. So I think I've got I've got this one example that hopefully will help. Okay. So, okay. So let's say you've got a diffraction grating and you've got 10,000 lines per centimeter in the grating. So here's a picture of the grating here. It's not showing you all the slits because there's just like so many of them. Okay, so this is like, don't be confused here. This is like a picture of like the exact same thing as this. It's just that they're not showing you the slits. Okay, because there's just so many of them. Okay. So what we want to know, suppose you have one, okay, so there's 10,000 lines per centimeter. So we're going to have to find the distance between the slits. Okay, because it's giving us like how many lines per centimeter. So to know the distance between each slit, we would have to take like 1 centimeter and divide it by like, is it 10,000 slits? Right? That will give us the distance between the slits. Okay, so that would be the first thing to do. And then okay, so the screen is 2 meters away. Find the angles for the first order diffraction of the shortest and longest wavelengths of visible light. So basically what it wants us to do is it wants us to find the angle, this angle here, between the central maxima here and um, like the m equals 1 fringe. Okay, because like within the m equals 1 fringe, all the colors separate out. So at one end here, you've got violet, and at the other end, you've got red. So it wants us to find like the angle between the central maxima and the violet, like where the M equals 1 fringe starts with the violet and where it ends with the red, if that makes sense. Okay, so all right, so we need to kind of know what the wavelengths are for violet and red to be able to solve this. So first of all, we know that the bright fringes, so bright fringe, obeys the same condition as it did for the double slit. So d sine theta is the condition for constructive interference, where the path length difference between any two rays is just some integer multiple of lambda. Okay. So that's like this is the condition for constructive, and that's where the bright, like that's where the bright fringe is. Okay, so and we're interested in the m equals 1, 1. The m equals 1 because they say the first order diffraction. Okay. Okay, so the wavelength, and you can just look this up for violet. I'm just going to use V for violet, is 380 nanometers. And the wavelength for red is 760 nanometers. Okay. So the first thing, oh, and we should calculate this out. What's the distance between the slits? The distance, so I need to divide 1 centimeter by 10,000. So I'm going to get 1 times 10 to the negative 4 centimeters, which is the same as 1 times 10 to the negative 6 meters. Okay, so that's D. Okay, so I've got like kind of on the left side everything I need. So now let's like calculate it out. So let me do it that up here. So sine the angle, and let me do violet first, is just going to be equal to, so if I just take this formula and I rearrange it and I isolate sine theta, then it's just going to be m, which is 1, times the wavelength of violet divided by the distance between the slits. Okay, so m equals 1 because it's the first order fringe. The wavelength of violet is 380, so that's 3.8 times 10 to the negative 7 meters. And then I'm going to divide that by the distance between the slits, which is 1 times 10 to the negative 6 meters. And I get 0.38, but that equals sine of the angle that I'm interested in. So to get the angle that I'm interested in, I need to take the inverse sine of 0.38. So that gives me, I worked this out somewhere, 22.3 degrees, 22.3 degrees. Okay, I go through the exact same procedure for red. So I say sine of the angle that red is. So that's like this angle here. Let me do it in red so you can see it. It's like this angle here from the central to here. Okay, that's that angle. Okay, just like for violet, it was like from the center to here. Okay, so this equals m equals 1, the wavelength for red divided by d. So this is going to be if you do that, I'm not going to do it all out for you. But if you calculate that, you should get like substitute in, 760 nanometers for lambda, m equals 1, and then the distance between the slits, and then you take the inverse sine of that, you get 49.46 degrees. Okay. So that's part A. Part B asks us, what is the distance between the ends of the rainbow of visible light produced on the screen for the first order interference? So it basically wants to know, like, what is this distance here? Okay, like this is part B. Why part B? Okay. So I can calculate out like the distance between the central like maxima here and each of the two like based on the angle that I just calculated, I can calculate the the y for the violet, so like the distance from here to here, okay, YV, and then the distance from the center to red, which is YR. Okay, and I can just use tangent for that, right? Because I know that the distance x is 2 meters, right? And so just like tangent of that angle is going to be y, which is what I'm looking for, um, divided by x, right? So like tangent here, let me do part B down here. So part B, so tangent of the angle for violet, right, is just opposite. So that's going to be like YV divided by adjacent, which is the x, the distance to the screen. Okay, so I'm looking for YV. I want to know like where that violet appears on the screen. So YV is just going to be x times the tangent of that angle, which I calculated in part A. So that's going to be 2 meters times the tangent of 22 degrees. Okay, and that equals 0.815 meters. Okay, and I can do the same thing for red. It's just going to be x times the tangent of the angle where red was found. So 2 meters times tangent of 49.5 degrees. So that gives me 2.3. I don't know why I'm using so many significant digits, but okay, so 338 meters. And what I'm actually asked is the difference, like is basically like the length of the whole rainbow. So I just subtract them. So this is just going to be the red minus the violet, which is 1.52 meters. Okay, so I think like this example just illustrates like, so you've got this like each of these rainbows equals like a higher order, it's only showing you in this picture like the m equals 1 and this is like m equals minus 1. Um, but like, depending on the grading and the distance between the grading and the screen, you might see like how big the screen is. You might see higher order, like m equals 2 rainbows and then m equals 3 rainbows. But like the point is that with a diffraction grading at each of the bright fringes, you see like a full rainbow. Okay. Unlike with the double slit where you just see a bright spot. Okay. Last topic. Last topic. So, the the Raleigh criterion is a way of using diffraction to understand like the resolution limit that we can see in optics. So like it's like just diffraction as like a concept, like because light bends around the edges, diffraction limits the detail that we can see or that we can obtain in images. Okay, like all optics have some diffraction limit, right? Like beyond which we can't resolve things. Okay, and it's a function of like the lens itself and the wavelength of the light. So like how like detailed we can see is it depends on the wavelength of the light that's like passing through some optical feature, like a lens. Okay, and that is referred to as the diffraction limit. So in this picture here, we see the effect of passing light through a small circular aperture. And instead of like a bright spot with sharp edges, you see this sort of like in this picture here, you can see this sort of like fuzzy edge halo effect surrounding like the bright spot. Okay. And this pattern, like the patterns, this pattern here, the pattern seen below is caused by diffraction. Okay, similar, very similar to that produced by a slit. So like when light passes around like any edge, um, and the wavelength of the light is in the same order of magnitude as the aperture, no matter whether it's a single slit or a double slit or multiple slits or a circular aperture, you have diffraction. And that diffraction causes this like fuzzy kind of like pattern that we see around the bright spot. And what's happening there is light from different parts of the circular aperture are like constructively and destructively interfering, which is what gives us this pattern that we see here. So let me just write that like light from different parts. It works the same exact way as a slit. It's just a little bit harder to understand when it's a circle, but just know that light from different parts of the circular aperture interfere constructively and destructively, and that's what causes which produces the the effect, the fuzzy edge. Okay. So the effect is most noticeable when the aperture is small. Okay, like the smaller the aperture, the fuzzier the image. And that's why like cameras that have really big lenses tend to take much like crisper, clearer pictures. Okay, it's because like the bigger the aperture, um, the the better the resolution. Okay. Um, so the goal here is to understand what the diffraction limit is of like say you have a lens and you want to know like what is the diffraction limit. So like in this picture, in this like figure 27.25, um like this part B shows you like two separate light sources that are shining through circular apertures and they're producing like overlapping like we can see that they're separate, right, but the because of the diffraction fuzziness they've sort of overlapped a little bit. Okay, and if we put those two sources even closer together, then we get something like in picture C where they can't really be resolved. So like picture A is a single source. Picture C is two light sources where the diffraction limit has made it look like it's basically just one. Okay, so there's something called the Rayleigh criterion, which allows us to basically calculate the diffraction limit of any optical system. Okay, so what the Rayleigh criterion states is that two images are just resolvable when the center of the diffraction pattern of one is directly over like the first minimum of the diffraction pattern of the other. Okay, so like that would be condition B here. Like in condition B, we can tell that we have two different light sources, right? And we can calculate what that angle is using this relationship here. So 2 points are just resolvable if they are separated by this angle here. Okay, I think that this picture down here actually like illustrates this the best for me. So say you've got two light sources, light source P and light source Q. Okay, and they are some like angle apart from each other. Let's say the light and you've got some lens like this here is a circular aperture. You can't really see, but here, this is a circular aperture. Okay. And it's got a diameter D. So the light from P is basically gonna go through, and then I've got a screen here. And it's gonna hit the screen and it's gonna have a diffraction pattern. And it's central, it's like its most intense peak is going to line up, basically in a straight line, like with the light that is going through the aperture. And same thing for Q. Okay, so like the light from Q goes through the aperture and makes this kind of a pattern. So they overlap. Actually, maybe I should do it in different colors just to like illustrate. Let me start again. Let me start again. So like, here, I think this will make it easier. So like, okay, so let's say that Q is red. Okay. And it's going, okay, so the light is going through, like all the rays fit through this, and there's some diffraction happening, right? Which causes this diffraction pattern that you see here. Okay, but it's most bright in the center, right? Which is where that peak is. Okay, let's say that the other one is green. Okay, like light source P is green. Okay, so the light goes from P through this circular aperture and it diffracts, right? So it causes this diffraction pattern, but the central peak is there. Okay. Sorry, I shouldn't have drawn. Just one sec, sorry. So the diffraction pattern for the light green is this one here. Okay, so there's like you can see the difference between the two peaks. Okay, so that would be like this picture here would be like this picture here in the middle. Okay, like it's just like each of these, like this one would be like the green peak, and this one would be like the red peak. I don't know if that helps you conceptualize it at all, but it's just like looking at it from a different angle. So in B, I can resolve the two sources. I can see that I've got two separate sources. So the question is like what is that angle like between the two sources, theta, so that I can tell that I've got two different light sources. And how I calculate that is very simple. It's just a function of how big the aperture is and what the wavelength of light is. Okay. So this is another picture that for me is not as helpful as the one above, but it just shows it to you like in a different way. So like um, it's the exact same thing. So there's your aperture, there's the light from object one, making like that intensity pattern. Here's the light from object two, going through that, making that. I should have drawn it like that, that where the central peak is there. And so I can tell that these are two separate sources. Okay. Um, so here's an example. you've got an optical instrument and it has an aperture of with a diameter of 2 millimeters, and I've got 600 nanometer light, and I want to know the angular resolution. So angular resolution is just asking for theta. It's just it's like, what is this? Like what is the angle between the two rays where I can still resolve them as two separate sources? Okay, so this is just like theta. Um, and the minimum resolvable separation, so that's like a linear distance for an object 4 meters away. Okay, so again, I like to draw it. So let me draw um, like a circular aperture. Okay, and let's say I've got two sources over here, and I've got a screen, say here, and the distance from the light sources to the aperture is 4 meters. And maybe let me make these different colors. Okay, so like the light from this one is gonna go here. The light from this one is gonna go here. There's gonna be like a diffraction pattern, like where the peak is in the middle like that. Okay, so there's some separation between those two peaks. And I'm trying to calculate this angle. Okay, so the first step is to compute that angle, which is referred to as the Rayleigh limit. Okay, so the Rayleigh limit is just 1.22 times the wavelength of the light divided by the circular aperture diameter. So this is going to be 1.22 times 600 nanometers, so 600 times 10 to the negative 9 meters, divided by the aperture, which is did it 2? Yeah, 2 millimeters. So 2 times 10 to the negative 3 meters. Okay, so calculate that out, and I get the Rayleigh limit as 3.66 times 10 to the negative 4 radians. Okay, the angle is always measured in radians. That's important to note. Okay, radians. Okay. Okay, so the second step is for us to find the minimum resolvable separation, given that the lens is 4 meters away. So we need to in step two, we need to convert the angle to a linear distance to know like how far apart could the two light sources be for us to be able to resolve them within that Rayleigh limit. So basically like to calculate this distance x. Okay. So x is going to be approximately equal to L times theta. Okay, where L is the distance between the two light sources and the aperture. All right, and that's just because of trig. I mean, it's just the relationship, the triangle relationship. So we can say that L equals 4 meters, and so we're going to multiply that by the Rayleigh limit that we got. So 3.66 times 10 to the negative 4 radians. And that equals 1.46 times 10 to the negative 3 meters, which is 1.46 millimeters. So with this aperture at this distance with 600 nanometer light, we should be able to resolve two sources that are 1.46 millimeters apart. Okay. So that's pretty much it. That's a an example of a problem that you might run across on the last section for calculating the limit of resolution. And yeah, that's pretty much everything I wanted to show you this week.